Okay.
We haven't really had any homework over the new stuff.
Okay, so good morning, everyone. So this is the example that we started last time. We have this section. We know the dimensions, we know the steel, and we want to plot the interaction diagram for the shown column. FC prime and F yield has to be given in order to be able to find the properties of that section, or the maximum, the nominal capacity of the section in terms of the compression force and the axial force that can be resisted by such a section. What we started last time is we found this point here for pure compression, okay? And then we are working on this point right now, the balance point, okay? For the balance point, the stress on the compression side for all those points. Every point on this curve, the compression, the strain on the compression side, on one side is in compression and is 0.003 because the section will fail when the concrete crushes. And then the difference between the points is the magnitude of the strain on the other side. So here it's 0.003, over here it's tension, it's not compression, and it's 0.002 in the steel, not on the extreme end of the section. So we did this here, the balance point. We drew the strain distribution according to the definition of the balance point. It's 0.003 over here, and in the steel it's equal to epsilon yield. And then we found that distance C and the distance A, which is beta 1C. And then the section has three forces: a compression force in the concrete, and a compression force in the steel, and a tensile force in the steel. Tensile force in the steel, since the tensile steel yielded, so it's F yield area steel. The compression force in the concrete is 0.85 FC prime AB. We already found A as a function of the distance C, and C we found it from the similarity of the triangles. And CS prime is Fs prime multiplied by area steel prime. Fs prime depends on epsilon steel prime. We did this, we created epsilon steel prime, so we found those three forces. So now, since we have the three forces applied on the section, the summation of them is equal to the nominal axial force applied on the section. Now, for this section, right now, if this is the column, we know that there is a Pn and an Mn applied on the section that gives that strain distribution, okay? So now we calculated Pn. Pn is applied exactly at the plastic centroid. So that's the location of the plastic centroid of the section. So that's the importance of finding the plastic centroid. Okay? It's the location over which that Pn is applied. So since our section over here is symmetric, so that plastic centroid is right in the middle of the section. Okay? So Pn is right in the middle of the section, so that means that this distance is 12 inches. Okay? So this is equivalent to the components. Okay? So that system over here is equivalent to the components. What are the components? We had steel here, so we had a tensile force, T, which was equal to 180 K. And we had a compression force in the concrete that was equal to, let me draw it, it's compression, it's 169.8, right? No, it's 515 K. And there is a compression force in the compression steel that is equal to 169.8 K. So those two systems are equivalent to each other. Pn and Mn resulted in those forces, okay, internal forces. So simply we said Pn is equal to the summation of those moments. And the moment of those forces about any point you choose is equal to the moment of those two forces about the same point, okay? So let's do this. Let's take the summation of the moment of both systems about a point of choice, okay? Any point you choose. So the point I choose over here is the tensile steel, okay? So taking the moment of the two systems, about the tensile steel. So for the first system over here, you have CS, sorry, CC, the compression force in the concrete, this 515, multiplied by this distance. How much is this distance? It's D minus A divided by 2. Plus CS prime multiplied by this distance. How much is this distance? It's D minus D double prime. And that's equal to the moments of those forces. Okay? So that is equal to Pn multiplied by this distance. Okay? So Pn multiplied by that distance, which is actually from here to here, that's 12. This distance over here was 2.5, so that's 9.5 inches. And a moment, Mn. The moment is not multiplied by a force. This is this moment about this point or about any point is just Mn. So now we know the magnitude of Cc, right? How much is Cc? It's 514, right? Multiplied by D minus A over 2, which is 16.09 inches. CS prime is 168.9 multiplied by D minus D prime, which is 19 inches. Pn is 509.6 K multiplied by 9.5 inches plus Mn. As you see here from this equation, you can find the magnitude of the nominal moment. So it's 559.8 kips feet. So actually, right now we know 559.8. So we already found Pn of this point, and we know this Mn, which is 559.8 kips feet. So we're plotting point by point, the two coordinates, Pn and Mn for each point. For this point, Pn was that magnitude and Mn is 0 because it's pure axial force. Now let's work on that third point. For that third point, it's pure moment. You only have moment, okay? Point 3 on the curve is pure moment. So when you have pure moment, that was covered in chapter 5, right? Your section looks like this. You have those 3 bars here, and you have a moment like this. So this is actually an analysis, okay, problem of a doubly reinforced section, okay, like the one you had on the test. So you just need to find Mn that can be resisted by this section, okay? So this is an analysis of a doubly reinforced section. So how do you proceed for an analysis of a section? First, you assume that the steel yielded or didn't yield. So here I'm going to assume that the steel didn't yield, although we start usually by the assumption that the steel yielded, but to save time here, I know it's not going to yield, so I'm going to assume that the compression steel didn't yield. If the compression steel didn't yield, so you equate the compression force by the tensile force, so T is equal to C. Why T is equal to C? Because there is no axial force, right? There is no compression force. So the compression, the overall compression force has to be 0. So the tension force has to be equal to the compression force. That's pure bending, okay? For the other points, no, there was C was not equal to T. C is equal to T only in beams because there is no compression force, okay? So the tensile force here is area steel F yield. The compression force, you have a compression force in the concrete, which is 0.85 FC prime AB. A is beta 1 C multiplied by B, the width of the section, B, plus the compression force in the steel, the compression steel, which is area steel prime, Fs prime. I can remove Fs prime and replace it by Es, the modulus of elasticity of concrete, multiplied by C minus D prime divided by C multiplied by 0.003. As you see, this is a quadratic equation, okay? Multiplying everything by C, you're going to have area steel F yield C, 0.85 F C prime, beta 1 C squared B, plus area steel prime Es C minus D prime multiplied by 0.003. It's a quadratic equation. You have to solve a quadratic equation. It's not a linear equation. So solving for C, everything here is known, okay, except C. Area steel is known, F yield is known, FC prime, beta 1, B is the width of the section, area steel prime, it's 3, number 9, ES is the modulus of elasticity of steel, D prime is known, so the only unknown here is C. So solving for C, it's going to be equal to 3.235 inches. Now you need to make sure that your assumption was correct. So making sure the assumption was correct, I need to calculate the strain in the steel and make sure that it's less than the yield strain. So epsilon steel prime is C minus D prime divided by C multiplied by 0.003. So that's 3.235 minus 2.5 divided by 3.235 multiplied by 0.003. So epsilon steel prime is 0.01694, which is less than epsilon yield. So assumption was correct. We assumed that the compression steel didn't yield, and actually it didn't yield. So now we know the distance C. We need to find the nominal capacity of the section. How much is the nominal capacity? So let's go ahead and find A. It's beta 1C. So A is equal to 2.75 inches. And then now we need to find Fs prime. Fs prime is epsilon steel prime multiplied by E modulus of elasticity of steel. So the compression stress in the compression steel is 0.01694 multiplied by 29,000 KSI. So Fs prime is equal to 19.77 KSI. Definitely it's less than 60 KSI. It didn't yield, so the compression steel didn't yield over here. You remember we divide our section into two parts. So there is an area steel. The area steel on the tensile side is divided by two parts. An area steel 2 that is, resisting the compression force in the compression steel. So that's equal to area steel prime, Fs prime divided by F yield. So this is all from chapter 5, okay? I'm just doing the same analysis as chapter 5. So that's 3 inches squared multiplied by 9.77 KSI divided by F yield, which is 60 KSI. So area steel 2 is 0.99 inches squared, and area steel 1 is the area steel minus area steel 2. So it's 3 minus 0.99, so it's 2.01 inches squared. Now you can go ahead and find the nominal capacity of the section. M nominal is area steel F yield multiplied by D minus A over 2 plus area steel prime Fs prime multiplied by D minus D double prime. Area steel is 3 inches. Sorry, this part, I'm taking a moment about the tensile steel. So this is area steel 1. Area steel 1 over here. So this is 2.01 inches squared multiplied by 60 KSI. multiplied by D, which is 21.5, minus A, which is, how much was A? 2.75, divided by 2, plus area steel prime, which is 3 inches squared, multiplied by Fs prime, 19.77 KSI, multiplied by D minus D double prime. So you can find the nominal moment. So this is 3,567 kips inch, dividing by 12, that is 296.4 kips feet. So that's the nominal moment, 296. So for pure bending for that section, if you have just the bending moment, okay, no axial force, that's the nominal moment that can be resisted by that section. So as you see here, it's the same section, but it can resist different combinations of compression force and axial force, okay? This point over here, this distance is 296.4 kips feet. So those are 3 points, okay? This is the capacity of that same section. Those are all the capacity of the same section. This is only when an axial force is applied. This is when the combination of an axial force and a bending that gives you a balance point, and here only a bending moment. To increase the accuracy of that curve, you need to add more points, okay? Because those are not, this is not a definite straight line. There is a small slight curvature over here. Here there is a curvature, okay? So if you just assume those are straight lines, this is a rough, okay, estimate, but to increase the accuracy of this, you add more curves here. So how to add more curves? We're going to take an example of adding one extra point on the curve over here. So that point over here is somewhere over here, okay? That's 0.4. We're going to add that point. What's the definition of 0.4? 0.4 is before the balance point. So the strain on the compression side is 0.003, but on the tensile steel is going to be less than epsilon yield, okay? So let's assume some strain distribution that, you know, would fit 0.4. So for 0.4, assume the following strain distribution. We have our section like this. We have 3 number 9 bars, 3 number 9 bars over here, and that's the strain distribution we're assuming. It's 0.003 on the compression side, and over here we're assuming 0.002 at the end, not in the steel. So in the steel, this epsilon T is less than epsilon yield. Okay? Is that permissible according to the ACI code? Yes. Okay? Only in pure bending where the tensile steel has to yield and the strain in it has to be larger than 0.004. But for combined action, the strain in the tensile steel can be any value. Okay? So from the similarity of the triangles, again, okay, you can solve for those distance. So solving for this distance, this is going to be 14.4 inches from the similarity of the triangles. Okay? And this distance over here is going to be the total width of the section is 24, so 14.5, 24 minus 14.4, so that's 9.6 inches. This steel over here, this distance, the cover over here is 2.5 inches. So subtracting 2.5 from 14.4, that's 11.9 inches. And again here, subtracting 2.5 from the 9.6, that's 7.1 inches, and that's 2.5. How did I find those distances? just knowing that the strain here is 0.003 and this is 0.002, this is 24 inches. From the similarity, you can find the distances, okay? Now you would need to know how much is epsilon t and how much is epsilon t prime, okay? So epsilon t prime from the similarity of the triangles over here is going to be 11.9 divided by 14.4 multiplied by 0.003. So that's 0.00248, which is larger than epsilon yield, so the compression steel yielded. The tensile steel didn't yield, okay? We know that the tensile steel didn't yield because the maximum over here is 0.002. Here it's less than 0.002, so it's less than epsilon yield. So how much is epsilon t? Again, from the similarity of the triangles, it's 7.1 divided by 9.6 multiplied by 0.002. So that's 0.00148. As you see, it's less than epsilon t. So now we need to find the forces, okay? As you see here.
Less than epsilon yield. Less than epsilon yield. Epsilon t.
So now we need to find the forces. This part of the concrete is under compression, okay? So we have three forces. We have a tensile force in the steel. How much is the tensile force in the steel? F yield area steel? It's F yield area steel if the tensile steel yielded. It didn't yield, so it's Fs area steel. You need to find Fs. And then here we have a compression force in the concrete, which is 0.85 Fc prime AB. And we have a tensile force in the compression steel, compression force in the compression steel, which is the area of the steel prime multiplied by the stress in the compression steel. How much is the stress in the compression steel? F yield, because the compression steel yield. So now just go ahead and calculate those one by one. So the tensile force is area steel, Fs. The area steel is 3 inches squared. Fs is the modulus of elasticity multiplied by the strain, epsilon t. So that's 3 inches squared multiplied by 29,000 ksi multiplied by 0.00148. So the tensile force is 128.8 K. The compression force in the concrete is 0.85 Fc prime AB. So it's 0.85 Fc prime is 4 ksi. A is beta 1. C, which is 14.4 inches, multiplied by B, the width of the section, which is 14 inches. So the compression force in the concrete is 582.6 K. Again, to differentiate between a tensile force and the compression force, we're going to give the compression force a negative sign. The compression force in the steel, in the compression steel, it's area steel prime F yield, so we have 3 inches squared multiplied by F yield, which is 60 ksi, so that's negative 180 K. As we did for the point for the balance point, Pn is the summation of the forces. It's T plus Cc plus Cs prime. So it's 128.8 K minus 582.6 K minus 180 K. So it's a compression force of 623.7 K. So that's the nominal force, 623.7. So plotting this point over here, 0.4, 600, as you see here, this is higher. This is 623.7 K. How much is the moment now? Exactly as we did for the balance point, we just take the summation of the moments about a point, okay? So we have the system taking the summation of the moment about the centroid, about the tensile steel, taking the moment about the tensile steel. So what we're going to have is we're going to have each force. So we have the compression force in the concrete. The compression forces in the concrete is 582.6 multiplied by its distance, which is 15.38 inches, plus the compression force in the steel, which is 180 K, multiplied by its distance, which is d minus d prime, so that's 19 inches. And that's equal to Pn, which is 623.7 times its distance to the tensile steel, which is 9.5 inches, plus Mn. From this, you can find how much is Mn, so it's 521.8 Gibbs feet. So 521.8. As you see, for that point, it was 559, so this point actually moves. It's on this distance, on this side. Okay? And you do this for different strain distributions. So we assume for this point, the strain on the left side was 0.002. Now we can assume it's 0.001. We're going to get the point here. We assume it's 0. We're going to get the point here. Okay? We assume it's 0.004. We're going to get the point here. Okay? And you repeat this, you get more points on the curve. Okay? Any question? So this is how you construct this interaction diagram. Okay? Now, let's move forward for our discussion of this interaction diagram. So the interaction diagram is a relationship between Pn and Mn for a given section. Okay? So let's say the section that we just analyzed over here, was 24 inches by 14 inches, and we had some area steel here. We had 3 number 9 on this side and 3 number 9 on that side. Okay? We plot the interaction diagram for that curve. It looked like this. Let me ask you a question. Now, if I decrease the steel, instead of 3 number 9 here, the same section, the same dimensions, the same FC prime, the same F yield, but instead of 3 number 9, okay, I decreased rho. I had 3 number 8. What will happen to that curve? Can you use that curve? Is it still valid? Definitely not. You have to plot a new interaction diagram. Okay? So if rho changes, what's rho? Rho is the percentage of the steel, area steel divided by BD. Okay? If rho changes, you're going to get another curve. So this is for 6 number 9. Let's say this is 6 number 8. What about 6 number 10? It's going to be, the strength is going to increase. This is 6 number 10. So just changing the steel for E, it's a new section. You have to plot a new interaction diagram. Okay? What if I change the dimensions? B or H? You have to plot a new interaction diagram. Okay? So instead of plotting a new interaction diagram, okay, the ACI code here, okay, plots those curves, but for a normalized one. So instead of plotting it for Pn, we're plotting it for Pn divided by Fc prime, area gross, which is BH. Okay? Instead of plotting it here on the horizontal axis, instead of plotting Mn, we're plotting Mn divided by Fc prime, area gross, H. So even if you change the dimensions now, you can still use the same curve. But if you change the steel, no, there is a series of curves here. Okay? And actually, those curves is given not in the ACI code, but it's given in an ACI publication. It's not here in your code. It's in an ACI publication, okay? And you can use this because it's at the back of your book, okay? So that's in appendix. In the appendix at the back of the book, you have those curves, okay? Those interaction diagram plotted between those two values. Instead of Pn and Mn, they are normalized, okay? So that you can use them for any section. This value over here is given the notation Kn, okay? And this value here is given the notation Rn, okay? So instead of plotting Pn versus Mn, we're plotting Kn versus Rn, just normalizing the moment by the dimensions and Fc prime, and normalizing Pn by the Fc prime and the dimensions of the column, okay? So let's take a look on in those curves over here. Those are at the back of your book, okay? So you have many curves. Actually, at the back of the book, you have 12 curves, okay? Those looks like this, okay? This is the first curve. If you have the book, please open it, okay? What you have over here is those series of curves that we just discussed, okay? Let me see, I guess in the presentation, in the slides, there is one that is clear that we can discuss here. So moving back here. So that's the one of the interaction diagram. You actually have 12 at the back of your book. Okay. What does this interaction diagram gives you? It gives you Kn versus Rn. Okay. We said here Mn divided by Fc prime area gross image. Here it's not giving Mn, it's giving Pne, which is Mn. The normal force multiplied by the eccentricity is the moment. Okay. What do we have here? We have a series of curves here. Can you see those series of curves? Okay. Each one of those is for different rho. So here, this one is rho is equal to 8%, and then 7%, 6%, 5%, 4%, 3 to 1%. Why didn't we plot any curves more than 8%? Because according to the ACI code requirements, rho cannot be larger than 8%, as we discussed in chapter 9. Okay? Why there is nothing below 1%? Because that's the limitation also according to the ACI code. Rho cannot be less than 1%, cannot be larger than 8%. What if you have rho that is equal to 3.5%? Where's the curve for that? Interpolate it. Just draw a curve in between the 3% and the 4%. Just draw a curve here. Okay? Interpolate it. What are those lines? Let's see, what are those lines? This point over here is the balance point. This line, as you see, those lines, there is a notation here, or a number given. It's Fs, the stress in the steel, the tensile, or the tensile steel, divided by Fu. So here, it's 0. So the stress in the tensile steel is 0. Here, it's 25% of Fu, 50% of Fu, 0.75% of Fu. Here, it's 100% of Fu, which is Fu. So this is the balance point. So any line, this line here, this point, this point, this point, all those points are the balance point on the curve. Okay? From these values, you understand how much is the stress in the compression in the tensile steel. Those lines gives you the magnitude of the strain in the tensile steel. The stress here in the tensile steel is F yield, but the strain is increasing. It's more than epsilon yield. For this line, any point on this line, the tensile strain is 0.0035. For this line, it's 0.005. Why do we care about this value, 0.005? Because if the strain is 0.005 or larger, phi is 0.9. So below that line, any point below on the curves, below that line, phi is 0.9. Over here, any point between this line and this line, the balance point, phi has to be calculated and interpolated. It's going to be from 0.9 here to 0.65 here. Okay? What about how much is phi here? 0.65. You don't have to calculate it, it's just 0.65. So here, phi is 0.65. From here to here, it's 0.65 to 0.9. And then below that line is 0.9. Okay? What other lines we have on this curve? This line is very important. K max. What's K max here? As you see on the vertical axis, we were plotting Pn, right? We were plotting Pn. According to the ACI code in chapter 9, we said there is a factor of safety alpha, right? That we have to take to account for accidental eccentricity, right? So actually that line K max is just multiplying this Pn by that factor of safety alpha, which was 0.8 for tied column and 0.85 for spiral columns. So as you see here, this is just multiplying this value is around 2, multiplying it by 0.8, it gives you a little bit less than 1.6 because this is less than 2. So this point becomes here. So you cannot be in this point. Even if you have a point here, according to the ACI code requirements in chapter 9, okay, that there is a factor of safety alpha to account for accidental eccentricity, okay, you have to move your point here, to this line. If you have a point here, no, you move it to here. Okay? That's K max. Pn cannot be larger than those values. So for a curve here, Pn cannot be here, cannot be larger than this value. Okay? So those are the interaction diagrams. So why do you need 12 interaction diagrams at the back of the book? Okay, so this curve here is for Fc prime equal to 4 ksi, F field equal to 60 ksi. We have at the back of the book different, okay? No, all of them are for 4 and 60, okay? But here you have gamma, okay? 4, right? 4 and 60. So here you have this value, gamma. Okay, what's gamma over here? If this width is h, the distance from the steel to the steel is gamma h. Okay? So that depends on how much cover. The more the cover increases, gamma is going to decrease, right? So this plot, this curve is for gamma equal to 0.7. At the back of the book, you have a series of curves. You start with gamma equals 0.6, and then 0.7, and then 0.8, okay? And 0.9, okay? Those are at the back of your book. So 4 curves for the same configuration here, okay? Just for different gammas, 0.6, 0.7, 0.8, 0.9. What if gamma is 0.75? Interpolate the values from the curve for 0.7 and the curve for 0.8, okay? And then you have another curves. Those are just 4. We're saying you have 12 at the back of the book. What are those 12? Another series of curves that are given. Over here is where the steel is distributed among the 4 faces of the column. And it's given the notation here R. The other one was L. The steel was only on the long sides of the column. There was no steel in between those 2 faces. Now you have steel in between those 2 faces, okay? If you have this steel configuration, those are the curves that you have to use for different gammas. Gamma 0.6, 0.7, 0.8, 0.9. So those are another 4 curves. And then another 4 curves for circular columns. If you have a circular column, okay, you have to use those interaction diagrams for gamma from 0.6, 0.7, 0.8, 0.9. Okay? So those are 12 interaction diagrams. They are given by the ACI, but not the ACI 318. Okay? It's given by, I don't remember the publication, but it's published by the ACI code, and it's at the back of your book. So in the exam, I will have those distributed to you. You don't bring your book, okay? I'll have those distributed to you so that you can use them, okay? So now, once we have those interaction diagrams, okay, we need to use them to analyze a column or design a column, okay? We have them, we can use them, okay, to design a column. So let's start with an example to see how to use those interaction diagrams to design a column to resist a given bending moment and an axial force. So that's example 10.3. So in example 10.3, we have a short column that is, so what does short column mean? Short, that there is no buckling, okay? So the dimensions of the column, we have a column that's 20 inches by a width of 14 inches. So we know the dimensions, or we assume the dimensions, okay? And this column has to support a compression force due to a dead load that is equal to 125 K, and an axial force due to the live load that is equal to 140 K, and a moment. It's an interaction or beam column or a frame, okay? So there is a moment due to the dead load as well that is equal to 75 kips feet, and a moment due to the live load that is equal to 90 kips feet. So those are the forces applied in that column. We need to design it. So what do we mean by design? Okay, we need to find the area steel that we have to provide to this column so that that column would be able to resist those forces. FC prime is 4 KSI, the properties of the material. F yield is 60 KSI. Where will you put the steel? The steel is only on the two faces, okay? So steel is distributed, or steel is placed on two faces of the column. So you're going to have some steel here and some steel here to resist those actions. Okay? The interaction diagram gives you a relationship between Pn and Mn, or Kn and Rn when you normalize those values, Pn and Mn. Okay? So now, how much is the moment that should be resisted by this column and the normal force that should be resisted? Simply, you have to, and here those distances, this is the cover over here is 2.5 inches, and the cover over here is 2.5 inches. Okay? So now, this column, you're given the dead load and the live load, or the compression force due to the dead load and the live load. So P ultimate is 1.2 multiplied by P dead load plus 1.6 multiplied by P live load. So 1.2 multiplied by 125K plus 1.6 multiplied by 140K. So this is 374K. For the moment, you just do the load combinations, M dead load plus 1.6 M live load. So this is 1.2 multiplied by 75 kips feet plus 1.6 multiplied by 90 kips feet. So that is equal to 234 kips feet. Should you use those in the interaction diagram? Is the interaction diagram a relationship between P ultimate and M ultimate? Yeah, okay. For the normalization, you divide by the area and FC prime. But what value do you divide by FC prime and Pn and Mn, okay? Not P ultimate and M ultimate, okay? As you see here, the curve that we drew, it was Pn, not P ultimate, Mn, okay? Not including the factor of safety, okay? So I actually have to divide those values. I have to find Pn. Pn is P ultimate divided by phi. Mn is M ultimate divided by phi. How much is phi? Phi is unknown. We said there is three regions. It can be 0.65 or any value from 0.65 to, sorry, it can be 0.9 or then from 0.9 to 0.65, right? We had this here, we had the balance point here, and we had epsilon t equal to 0.005, right? So here, if you're here, p is 0.9, from here to here it's 0.9 to 0.65, here is 0.65. So how would you know? You have to assume a value. What value do you think you would assume?
0.65.
Why 0.65?
There's more region 0.69.
Exactly. The larger part of the curve is on the 0.65. So just assume phi equals 0.65. And then you have to check this assumption. Okay? So Pn is 374K divided by phi, which is 0.65. So here, assume, okay? And again, I put this word in the box. This is an assumption you have. Once you assume something, you have to check this assumption later on that your assumption was correct. So Pn is 574.K. Boy, 575.4 K. This over here, 234 divided by 0.65, it's 360 K. So now we have Pn and Mn. Okay? To use these curves, we need to normalize Pn and Mn. Okay? Normalize them by Fc prime, area gross, and normalize this here by area gross H. So let's do this normalization. Kn is Pn divided by Fc prime area gross. So 575.4 K, 4 KSI. Area gross is the 14 multiplied by 20 inches, so 0.513. It's unitless value. Rn, it's Mn divided by Fc prime, area gross H. Here you have to be careful for the values, the units. Here you have 360 Gibbs feet. 360 Gibbs feet divided by Fc prime, which is 4 KSI, multiplied by area gross, which is 14 by 20 inches. H is 20 inches. The units are not consistent, so I have to multiply here by 12 to change the moment from Gibbs foot to Gibbs inch. And then Rn is 0.193. This is Kn and Rn, okay, that are applied on the column. Now, you just need to use the curve from that curve, okay? But which curve? You have different gammas. Which gamma you're going to use, okay? So we have to calculate gamma over here. So gamma is this distance. How much is this distance? It's 15 inches divided by this distance, which is 20 inches. This is from the, the curve. So gamma is 0.75. 15 divided by 20, so it's 0.75. So you actually have to use gamma equals 0.7 and 0.8 and interpolate. So over here, this is for 0.8. You plot the value of Kn and Mn and see how much rho is required. As you see rho here, this is 1, this is 2%, so it's 1.85%. And then here, you have for 0.7, you plot Kn or N, and you get this point. It's between 2% and 3%. You interpolate the two values, it's 2.2%. Once you find those two values, you just interpolate. So that's for 0.7, that's for 0.8. You find the average, so that's rho required to be able to resist that moment. Once you find rho, you multiply that rho by BH, you find the area steel, and then you go to the tables, find the number of bars required, okay? And this is a column, okay? So you have to do all the checks for the column, okay? The spacing between the bars, you have to decide for the ties, it's a column, okay? So all code requirements that were given in example 9.1 have to be checked. So this is how you design for the area steel using those interaction diagrams. Okay? Any question? Okay, so thank you.